Hello, this is the next video in a playlist that I'm calling Probability Theory, and we're going to look at sub-sigma fields in this video. Now, a quick definition: a sub-sigma field is a smaller sigma field that is a subset of the principal sigma field. And in statistics, this is so important, from conditional probability, conditional expectation, to sufficient statistics. And so the two videos that we're going to review will be used over and over again in these videos. So theorem 1, let omega u be measurable, and that means u is a sigma field of the subsets of omega. Now let A be any element of u, the sigma field, and define u of A to be all the sets C, such that C is the intersection between B and A, such that B is all the elements of the sigma field U. Then A UA is measurable, and that means that UA is a sigma field of sets of A. And the proof goes like this. First of all, we must show that UA is a sigma field of the subsets of A. So A has to be in it. And A is equal to A intersect A, which is an element of the sigma field. And so by definition, A is in U of A. Next, we have to show it's closed to complementation. So let D be an element of UA. Then D is equal to B intersect A, for some B in the sigma field U. Now, since U is a sigma field, that means B complement is also in the sigma field. So then D complement is equal to B complement intersect A, and that's part of U of A. And to show that it's, explicitly the right answer, if we look at D union C, and then we write out what D is and D complement, the intersection and union is back to A. And a picture of that is if we have A and B, A intersect B is D, A intersect B complement is D complement, and D complement union D complement is A. So it is complementation relative to A. So it is closed under complements. Now it has to be closed under infinite union. So let's let D1, D2, be elements of UA. That means each DI is written as BI intersect A, and an element of UA. And this for all I, right? This relationship has to hold, because in order for these to be in there, this is true. Now the infinite union of the DIs is equal to this, BI intersect A, infinite union. But this is equivalent to the infinite union of the BIs intersect A. But since this infinite union is part of the sigma field, then we know that infinite union of DIs is in UA. And hence, UA is a sigma field of subsets of A. And UA is measurable. Now the next theorem is this. Let C be a class of subsets of omega, and A a subset of omega. Now A does not have to be in this class. It can be or it can't be. Now if we know that it is, there's other certain properties that we may cover. But let C, script C intersect A, be all the sets B intersect A such that B is in this class. Then the sigma field of subsets of A of script C intersect A is equal to the sigma field of sets of the class, relative to omega, intersect A. Now where, sigma of A is the minimal sigma field of subsets of A over the class of, script C intersect A. What that's saying is A, rather than omega, is regarded as the entire space. And this is quite intriguing result. So the proof goes like this, that in order for these to be equal, we're going to show that this these sets are a subset of these, and then we'll show that these sets are a subset of this, and in order to be subsets of each other, they have to equal. And that's kind of the approach that we're going to use. Now, since the class of sets is a subset of the sigma field generated from the class of sets, right? This may not be a sigma field. In order to make it a sigma field, you have to add sets to it, and that's why it's a subset of the sigma field. That means if we intersect A on both sides, that this is a subset of that. Now, from Theorem 1, we know that this piece is a sigma field of subsets of A. Therefore, if we if we generate a sigma field from these and a sigma field of these with respect to A, then the relationship still holds. This side's a subset of this side. So therefore, the sigma field, with respect to A of C intersect A is a subset of this sigma field. But then you might ask, well, why didn't I put a sigma A of this? Well, this is already a sigma field of subsets of A, so we don't need to put it there. But this is a subset of that, and that's part of what we wanted to show, right? That this is a subset of that. Next, we're going to show that this is the sigma field of C intersect A is a subset of this sigma field. Now, to do that, we're going to pick an arbitrary element in this set and show that it has to be in this set, and that means that this is a sigma field of that. A subset of that. So let B intersect A be an element of this. So, and this is for all B in the sigma field generated from the class, right? B in this. Then we will show that this element is also an element of this set. Now let S be, we're going to generate a class. So let S be equal to all the sets B that are elements of this sigma field such that B intersect A is an element of this sigma field, sigma of A, script A intersect B. Now, I'm going to leave this next step as far as homework to you, and it's quite straightforward, right? We're taking sets from this sigma field and requiring them to be a part of this sigma field. But since both of these are sigma fields, it's actually quite straightforward to show that S is a sigma field. And you do that by showing the 3 steps, that A has to be in it, it has to be closed under complementation, and the infinite unions have to be a part of it. It's really straightforward. But by definition of S, we know S is a subset of the sigma field generated from the class C. And the reason this is true is, remember, we're taking all the sets that are here, and they might not meet this condition, right? So not all elements B of this may make it. So S has to be a subset of this sigma field. Now, since the class is a subset of S, and let's explore that a little bit. Since the script C is a subset of S, so here script C is a subset of this sigma field generated from script C, right? We know that. But let's concentrate the B's only in this class, script class, not in the sigma field, right? C is in this sigma field. So if we restrict the B to be that, then the sigma field generated from the class intersect A, right? B is in this class already. And then we generate a sigma field from it, and then it grew. So this has to be an element of that, right? So the whole entire class is a subset of S, right? Now if we take the sigma field of both sides, generate a sigma field of both sides, then we know that this is true. But wait, We just said S was a subset of the sigma field, and the sigma field is a subset of S. So hence, those two are equal. S is equal to the sigma field generated from the class. So thus, this sigma field generated from C intersect A is a subset of this class, right? So this set is equal to the sigma field of C. So that means every element in this class is part of S, right? They're equal. Then, so that means if we take B intersect A, but B is every element of this sigma field, it may or may not be in this, but it's clearly a subset, right? Some of them make it, so it's a subset of that. But wait, they can't be subsets of each other. We showed in step 1, this is a subset of this, and now this is a subset of this, so therefore they have to equal. And that's what we wanted to show. Well, I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.